Go ahead.
But I cannot move. Ah, yeah, no, it works.
You
Okay,
can
I'm
use it.
sorry for the hiccup. Yeah. So the importance of wireless charging is increasing clearly, as you see here by this market study. And this is various methods combined, these numbers, because as you probably know, there are various ways to do wireless charging. So you also have inductive and resonant methods. Inductive methods you may know very well, like you may be charging your smartphone every day in this way. Also inductive charging of cars makes use of this first method. And that's also why this first method, inductive wireless charging, is having such a high market share. But you also see there is the expected tendency that the relative importance of RF wireless powering will be increasing significantly over the next years. So what does it mean? So we have a base station or an access point and various sensor nodes. And we want to combine in the downlink, so from the base station to the sensor nodes, both wireless powering and data. And then on their turn, the sensors will also send back data to the base station. So in a nutshell, there are two main challenges. One is the optimal design of such a sensor node. And on the other hand, as I will explain, also the type of modulation technique used is important because we need to find an optimal balance between the quality of wireless powering and data transmission. And as you can intuitively expect, so the requirements are not the same for both types of users. And when we talk about downlink, wireless power and data combined, a term that's used for that, an acronym is SWIFT, so simultaneous wireless information and power transfer. Yes, so I will, and I try to keep it high level because I expect the audience to be diverse in terms of their field. Yes, I will talk about the hardware architecture and then also about the waveform design. And along the way, give some examples that were developed in our research group at KU Leuven. Now, in a classical node, so in a classical receiver, you need a down conversion block and a decoder to receive data. Now, to receive energy, the usual way to do it is you make use of a diode that converts the RF signal into DC signal due to the nonlinearity of the diode. And then by adding this low pass filter, you filter out the actual DC component. So in first instance, you may say, well, in our node, we put the two blocks in parallel, and then various methods can be considered. On one hand, time switching, so that alternately you either receive data or you process the incoming waveform for energy harvesting. Or you can also do a split in terms of power, so that, for example, 80% of the received signal is going to the harvesting part and the other is for data, or any other ratio that may work well for the application. Now, we feel that this is not an optimal architecture for the node because we have two branches in parallel. And to achieve down conversion, you need a mixer, you need a local oscillator, and all these active components, they consume power. So that's why in this community, the following topology is being researched, namely where the same architecture like we have here, it's also used to down convert the data and well, as a demodulator. And actually it makes sense because if you look to the schematic, it's equally well the schematic of an envelope detector. So that can be used for measuring, determining an AM modulated signal, for example. So that's what we call integrated receiver, not necessarily from the point of view of having an IC design, but from the point of view that the RF signal travels through this first block in red, and then it gets split in baseband between the power management unit and then the decoder for the data. Now, what are key performance indicators for wireless power transfer? Well, you want to have, of course, high energy efficiency. The maximum DC voltage that you can generate should be high enough such that you can power the various active blocks in the sensor node, like especially the sensor, for example. But also it should work well at low input powers. And that's logical because we know if we just look to ambient levels of RF signals in our environment, the power is low, in the order of minus 30 dBm. But yeah, it depends, of course, on whether you're close to a base station or not. And in case of intentional powering, the power levels are also low because you have to take into account the free space losses. And that's somehow contradictory to a diode operation because for a diode to operate, you need to be able to switch it from off state to on state. So you need a certain amplitude. And that's why also the actual signal matters. So I have here on the right-hand side an example of a multitone, so like at RF frequency to have four frequency components, for example. And when you evaluate that in time domain, so if all these signals have equal phase, then you end up with a high peak, or in technical terms, a high peak to average power ratio. And this high peak is of interest to drive the diode in forward condition, and in this way to convert RF energy into DC. But you can imagine that this optimal condition is not so optimal for data communications because there often you want to drive the transmitter amplifier not too strongly. So there you want to avoid having high PAPR signals due to otherwise nonlinearities and distortion in the power amplifier of the transmitter. But these are the key performance indicators for wireless power transfer. Then what about data? Here it's schematically represented in a simple way. So for data, we need multiple tones. Here, the most simple version, 2 tones. The diode will also convert it. And in this example, it means that the 2 tones end up in a baseband signal at the difference frequency. And so by varying amplitude, phase, and frequency offset, that's a way to have data in this approach of using the diode. And for well, data communications, the KPIs are, of course, the data rate and the bit error rate. Then finally, for the uplink data, and again, we want to do it as energy efficient as possible. So actually, the base station in this case will send the carrier signal, and then it's designed in such a way that the reflection coefficient is changed according to the data you want to transmit. So the like the various bits correspond to a particular setting here of the switches in this simple example. And so by varying the reflection coefficient, the reflected signal will change. And that's represented here by this figure. So the envelope that you see here is actually modulated by the modulation that is introduced over there. Similar principle is very well common in RFIDs. So what's the difference between this work and RFIDs? In RFIDs, you have no local energy storage. So you send the signal and you immediately get back the response. But here we have more flexibility because the energy can be stored locally and then used in a particular way. So for the uplink data, you want, of course, to keep the power consumption as low as possible. What do I mean here with power consumption? Well, you need some electronics to control the switch, so that requires energy. It's data, so data rate, error vector magnitude are important again. And finally, the range, because the difference with RFID is that we want to reach higher ranges, so higher distances, by using this approach. So by the fact that you store energy on the node and then use it in a way to increase the range. And so it should be clear that there is a trade-off needed between wireless powering and data communications, and it can be done by the architecture of the node and the signal modulation design. So regarding the node architecture, and again, I don't want to go into too many technical details, but the node consists of various parts. So essentially, you have the rectifier, that's the diode, and then you have the backscattering part, and you have another baseband part, like the power management unit, the actual sensor. And well, in our research group, we work on all these aspects, but now I'm going to focus only on the RF part in the examples I will be presenting next. So an approach that my student proposed, and he even won the best paper award for it, is to make use of frequency division, well, multiplexing, FDD, by which the signal for energy harvesting is in one band, and the signal that will be used for backscattering is in a slightly different frequency band. And the challenge is to keep these two frequency bands as close as possible, such that the antenna can still be a pretty narrow band antenna, that there is no need for a multi-band antenna. And so this is the signal that will be sent out by the base station. Here you see a particular design by my student. Usually we work on printed circuit boards because we want to show the principle, well, the concept. Of course, one can also proceed to full-blown IC design once the feasibility has been shown. Now, part one is where the antenna would be connected. Then we have a part for the energy harvesting, and here a part for the backscattering. And in this example, so the controlling of the reflection coefficient is done here by applying a DC voltage to a transistor. And what is then performance that we are looking at? Well, we want to have optimal backscattering results in the backscattering band and optimal energy harvesting results in the energy harvesting band. So that's what we are evaluating here. And this is the magnitude of the reflection for different settings of the reflection coefficient. We clearly see an impact in the backscattering band, whereas the impact in the energy harvesting band is intentionally kept low because you want to have constant harvesting and you don't want that the two functions impact each other too strongly. And then the other way around for energy harvesting. So you want that you obtain the maximum possible power conversion efficiency independent of the data symbols that are being backscattered. And in this design, it happened to be that at another frequency, due to the microwave design, the obtained efficiency was even higher. And when we do then a test by which the base station sends 2 tones, then we could also evaluate that we have different backscattering levels depending on the setting of the transistor. And the power consumption of the transistor is a few microamps. So that was combining backscattering and energy harvesting. But what if we now want to do SWIPT, so also having data in the downlink band? So it means then that we have, well, a multitone in the downlink band. And in this case, you see there is no signal in the uplink band as sent by the base station. Because actually the modulation in the downlink band will have as result that the diode creates third-order intermodulation tones, and that's what we are using for the backscattering. And this is a recent result that we will present at a conference in a couple of weeks. This is the full-blown circuit, and the open step essentially means that we are sending back the nonlinearity frequency signals to the diode in order to improve further the performance, such that we have the third-order intermodulation product that we can use it for backscattering. This is the design with the various parts, matching network to interface with the antenna, energy harvesting part, backscattering part, and then a comparator to decode the received data signals. Also here, similarly, we obtain good performance in the energy harvesting band, so good conversion efficiency. And we also see that in the backscattering band, indeed, we are able to control the amplitude, and that is a measure for the different well, data bits that we would be sending. And here, final result of an actual measurement on an oscilloscope in order to evaluate that if this is the RF incident signal, how does then the signal looks like after the diode, and then finally also after the decoding. Of course, this figure is not very clear. One has to zoom in order to analyze the data in more detail. In terms of waveform design, so far I talked about the hardware. I have a cooperation with the University of Technology in Sydney. So I have a joint PhD student over there. and to show what kind of work this involves. So she is working with more complicated modulations than the two-tone I have been talking about so far. So she's working on face modulations. And you see here that the different tones at the left-hand side, they are not equidistant, and that's intentionally because after the down conversion by the diode, you want to end that the different spectral components, so corresponding to the different frequencies, that they end up at different frequency bins. And then the data can be further processed. So phase modulation means that you apply phase modulation to each of the tones. And then the question is which phase range would be optimal? Because if you keep the phase range pretty small, like the first example, minus 45 degrees to plus 45 degrees, then actually the PAPR will be higher. And higher PAPR means higher conversion efficiency compared to a case where you have a wider distribution of the possible phases, because then the conversion efficiency will be less. But on the other hand, this case is good for bit error rate because then the phase margin is larger. And that's here also illustrated. Well, these are our simulations. That the bit error rate for this third case, minus 180 to plus 180 degrees, is better compared to the one of minus 45 to plus 45 degrees. So this illustrates again the trade-off that one has to make between either having better performance for energy efficiency or to have better performance for data communications. And also related measurements have been done to support the simulation results. Okay, let's see if I can still talk a few minutes. So the next topic is indoor light harvesting, and at first sight it may look a very different topic, but actually I will explain there is an analogy. And also here I will talk about both harvesting energy from light and also light communication. So what is the scenario? So far I talked about the case at the right-hand side, where the access point is sending power and data to the node, and the node is sending back data to the access point. But we have lamps in our homes, so we're focusing here on indoor light. We can use solar panels in order to harvest the light energy. And also light communications is becoming possible. So that's actually a whole research branch. But what in terms of first the energy harvesting? So if we look to the model of a solar panel, then actually it looks pretty similar to the schematic I've shown before. Namely, you have a diode and a low-pass filter. The main difference is, of course, that now you have a photon current exciting the operation of the solar panel. But as we know from the research in the community, that you can improve the energy efficiency by manipulating the waveforms. So the question we ask ourselves is, can the same be done for solar cells? So not using the straight DC light, but to change the waveform of the light. And that's indeed the case. I have here, one example. So this is a simulation result of DC illumination, so constant illumination of light. It's a constant, so the PAPR will be low, and then also the photon intensity will be low, because we are making here a comparison for the same value of total average power. And for the case of photon current of 0.9 milliamps, you see the harvested power is around 1.6 milliwatt. But then if we apply a multitone, like what turned out to be very good for RF wireless powering, then we indeed see an improvement. So now with the same conditions, instantaneously we can go to more than 2 milliwatt. Because the PPR will be, well, obviously better than compared to a pure DC signal. Now in light, you can go further. I mean, if you use many multitones, in the end you get a square wave. And because we are exciting here at low frequencies in the kilohertz range, it's possible to actually work with pulse width modulation signals, or PWM. And you see here the result is even better as with the multitone, because you can play with the duty cycle and in this way have instantaneously higher photon intensity. And as I tried to explain before, that's optimal for good operation of the diode. Now that were simulations, but we also tested it. So Basina was asking about ARFTech before. So ARFTech is the well, it's a professional group, non-profit, on microwave measurements. So in my work, I attach a lot of value to measurements. And the fact that I was president for the both aspects at the same time, it was due to well, unexpected coincidences. But I think it's also an example of the multitasking that we as women can do. Okay, back here to the example. So we have the transmitter. So this is very simple, well, in-house made design. So where we apply pulse width modulation to an LED, and here the corresponding solar panel as the receiver. And we compared here, well, based on measurements, what can we get if we supply 1 watt of power? So to either the base station or to the LED driver. And as you can expect, the power level is higher for light than for RF transmitted power. It's about a factor of 2 for DC. But you see, you can improve it better, improve it further if you use a dedicated waveform. Often you hear that indoor light powering, it's well, the performance is not good. Well, but by applying such kind of optimal modulations, you can actually obtain well, better performance, and then it's becoming of interest to use that approach. And what about then combining it with data? So there the idea is similar as with the RF harvesting, namely that essentially the low pass filter after the diode, you don't make the cutoff frequency too low. Well, that's what you need for energy harvesting. But if you make it wider, you can also catch the ripple, and actually the data communications is in the ripple. So the same idea is possible for light, but that's still ongoing work. So to improve actually the bandwidth of the solar panel, and to continue, of course, the work on optimizing the PWM waveform. Okay, this brings me to my conclusions. I tried to explain that in order to improve performance of light and RF energy harvesting, it's for sure worthwhile to check the and to think carefully about the design of the waveform. So we demonstrated the combination of SWIT and backscattering. Often in literature, you see only two functions, but we managed to demonstrate the three functions simultaneously. And what about the future? So we think hybrid energy harvesting is likely the way forward, by which most energy will be harvested from the most promising resource, like light. But not always there is light available. So the RF harvesting would then serve to supplement the energy that was harvested by light. What is the challenge? Well, it's standardization, because in order to improve energy harvesting, one would like to increase the transmit power, but then of course one comes into health issues and other standardization issues, because so far standardization has been focused on wireless data communications, but standardization related to, well, long distance wireless powering, so I'm not talking about charging cars, that's still in the very beginning. Okay, and this was my final slide, so I would be happy now to answer any questions.
Thank you very much, Dominique, for this fascinating presentation. And I wanted to, before I will open for question, I wanted to comment. Congratulations on being IEEE Fellow, in particular at the level of associate professor, which is, of course, extraordinary. And also congratulations on breaking ceiling for women by being president, first to a female president of IEEE Microwave Theory and Techniques. So this, I consider those as huge achievements, but also I am pleased to hear I've been involved in IEEE Fellow for a long time. So it's nice to hear that nice story, impact that fellow made impact on your local career and professorship and so on. So this is very important feedback for IEEE fellows. So when they have to decide junior person or senior person and so on, it's such a nice feedback that this makes huge difference in career, professional career. So I have also small question by listening to you and by seeing, first time you did that, my question is how you were inspired, how you were motivated for joining this kind of area of research. Who inspired you or what inspired you and how it happened? Just if you can say briefly.
Oh, actually, and that may actually be a drawback, I'm easily interested in many things. So as you also mentioned in the introduction, I always like to learn new things. So that's why I'm busy on 3-4 research tracks in parallel. So well, I think when I was well, how to say, when I was a high school student, I can tell you one more anecdote. So I was in an only girls school. So at that time, it was still the case in my part of Europe. And there was also my own city.
By the way, me too. I also
Okay.
I also attended all girls high school.
Yeah. And well, in the same city, there was, of course, also a high school for only boys.
Yeah.
And they got after class additional training and preparations for the entrance exam for engineering. But in the girls' school, it didn't happen because we were so few. Actually, I think I was the only one in my year who was interested. Well, who was interested in continuing in sciences. And then I did get some help from my mathematics teacher, and I passed the entrance exam, even though I did not have the additional weekly, drilling classes for mathematics for the entrance exam. And then I said, okay, I passed, so let's proceed with the studies. But overall, of course, I got a lot of support from my parents, and I also have an older brother. But I like things related to microwave and as I mentioned, related to experimental work. So that on its own, if that's a challenge, that's of interest to me.
Oh, this is great. Oh, this is great. If you have to take away something from your lecture, this would be my takeaway.
Okay.
Challenging. But you have a question: how to get into postdoc in IoT?
Postdoc, do you mean in general or?
After PhD, you mentioned after PhD, we commonly in the United States is that postdoctoral,
Well,
position.
that's right. So the postdoc was actually supported by the Flemish Science Foundation, so the equivalent of NSF, but in Belgium. But my PhD was about nonlinear measurement techniques. So because IoT, I think the term may have existed yet, but it was still very, very far fetched. So my research, well, you still sense I have interest in nonlinear aspects. So how did I get? Well, I think I interfaced with people at conferences, and I was actually lucky to have an experimental setup from a major equipment vendor at that time. And actually NIST then at some point got interest in also this new experimental setup. And then they brought me over, and in the beginning I was kind of training them, but over time, of course, they did very nice work with that instrument.
Yeah, thank you. And any other questions? Please unmute yourself and ask directly question. If we have, yeah, Cinzia.
If I may. So thank you very much, Dominique. It was really very, very interesting and inspiring. So you mentioned two things, actually. The very first one is that you are chairing this committee, which is interdisciplinary, society. I just wanted to know a little bit more about that, because of course I would be interested in bringing in my society, which is the nuclear plasma science. But I'm wondering if there would be, how would be other type of societies which are not really strictly related with what you are doing, being able to contribute. And my second question is a little bit more technical. So can you tell us, beyond light harvesting, if there would be other kind of harvesting? Energy harvesting, I think, would really be part of the most general energy situation, let's call it, that we have right now. Would we have other way of harvesting energy, for example, by using vibrations or temperature difference?
Yes, so and there are techniques that are already being researched as well. So vibration, temperature, And then it depends on the type of sensor, because vibrations is typically used in for industrial applications, because then it can be put on the devices. Heat as well, or for wearables. So if persons carry wearable sensors, then based on their movements, they can charge. Like my watch, it's also charged based on my movements, so there is no battery in it. And it depends on the use case, which of these techniques are the most optimal for the particular situation. And there is also another strong research area. I'm not directly involved myself, but it's solar power harvesting. So it's harvesting from the sun, and there are very big installations. And yeah, I mean that could be a potential in the future. And then the first question. So well, when I was MTTS president, there was actually already interest strongly on wireless power transfer in our society and also in PELS society. So there was one champion, let's say, in our society who made the bridge with the PELS society. And the origin, it started that each of us, we had a dedicated conference. And then we realized, yeah, but there is overlap in terms of scientific interest. So let's do the two conferences together at the same location, but independently organized. And over time, it turned into one merged conference. But then the idea was also, can we take it further? And then a colleague from MTTS Society, he submitted to IEEE Future Directions a proposal for a small project. So it's not initiative, it's not technical community, it's like the first step. And when you are evaluated there, it's normal and it's fully correct that you try to involve other societies who may be of interest, who may have interest in that field, and that's how the others became involved. So, but that small project ended at the end of 2021. And we got about like $10,000 or so, and we used that for a student design competition, so really for the members. And I was a member up to that point, and then I was asked to take over from the chair at that point. And now we are brainstorming about the next step. So would we try to go for an IEEE initiative or a technical community? They also have technical community 2.0, or just stay as an informal discussion group who meets once a month on on WebEx for a conversation.
Right.
So that's in fact how it works.
And Control System Society has huge activity in wireless networks. So I will be in touch with you. But
Sure.
Ramalata, you can unmute yourself and ask question. You can, of course, she will be our next speaker, but she has question. Can you tell some of the environmental impacts of wireless networks? Ramalata, you can absolutely unmute yourself and ask question directly.
Thank you, Muzana. So, Dominique, first of all, thanks for that wonderful talk. So, I just want to know how much of environment impact we are getting because of the wireless networks. As you know, right now we are embarking on so many advancements in these networks, and how much of environment impacts are realized actually, because I have been hearing so many myths about the endangered species for the, endangerment condition for the birds and other things. But is it true? I just want to know.
Well, I have, so I kind of follow the standards, but indeed you have you can read various opinions in the literature. So I do not do research directly on the topic myself, but and I'm assuming the regulators that they are doing a good job regarding that to protect the people. But for wireless power transfer, like one aspect we are looking into, and I didn't mention it in the talk, is to lower the power immediately if there is a person nearby. So we can detect persons in the environment. And when we see that the person is coming near to the beam of the wireless power, that then the wireless power transmitter gets shut down or goes to a lower mode. So I think that's maybe the potential for the future. So to make these systems adaptive in order to keep it safe as possible for for the people and for the animals.
Sure, I understand. Thanks, Dominique.
Thank you very much. And I don't see any other questions, so I will turn to Cynthia to close our seminar today. Once again, thank you so much for being with us. Congratulations on all this first time a woman doing all this and breaking ceiling for so many others. And
Thank you.
Cynthia, this is you. Thank you.
Thank you. So let me just join Bodzena for thanking you, Dominique. It was really very inspiring presentation, and I hope it will be really opening for more discussions and more collaborations among all the people who attended. I just wanted to also stress the fact that several people are watching the presentations offline because, of course, they are happening at different time of the day in different parts of the world, but we know that the recording is really watched a lot, and so you might really be receiving also contacts and communications from other members who will watch your presentation remotely. So thank you again. And it was a fantastic meeting you as well. And thank you, Bodzena, for your moderations, impeccable as usual. And to all the people who attended today, all our viewers, you saw that I posted all the information that I promised at the very beginning on the chat. So please go and look at that if you are interested. And see you in a couple of weeks again. So as already mentioned, Ramalata Marimutu will be our next speaker, the 24th of June. And so looking forward to seeing many of you again the 24th of June. So thank you, everyone. Thank you again to our extraordinary speaker, and see you the 24th.
And in chat, Dominique, you can read nice words. Thank you, congratulations, and great work, and everyone
and
enjoy.
Be welcome to contact me. So yeah.
Sure. Thank you so much. Thanks.
Bye, everyone. Thank you. Have a good
And enjoy your meeting in San Diego.
Thank you.
Thank you so much. Bye-bye.
Bye-bye. Have a great weekend, everybody.
And thank you, Joredna. Thank you for assisting us.
Thank you.